Hello and welcome back to my channel. Today we'll be discussing the second episode of the series on statistics, exploring statistics 2. Random errors, normal or Gaussian distribution. So quite a few words. Distribution, what is distribution? Distribution. What is normal and Gaussian distribution, and how all these are connected to errors which are random. So start with what are random errors. In fact, if you do any experiment, uh, all experiments contain this random error. Now, what is random error? There are two kinds of errors. Some errors are there which you can minimize or eliminate by increasing your expertise or experiences, or by improving the quality of the instrument, etc. But some are there, some variables which are beyond your control. So these are the random errors. Obviously, that random errors leads to some uncertainty in result or outcome of an experiment. But interestingly, the random errors individually, there may be so many random errors. Individually, they are mostly unidentified, or even if I can identify them, it is not detected. So then it's interesting to ask that why it's important then if you cannot identify, or even if you cannot detect. Problem is that yet when they are taken collectively, the accumulated effect of those individual small errors, that is detected. The accumulated effect is detected. And since the individual errors were random, so the outcome is also random, and it fluctuates usually around the average value. So for example, in this diagram, we are measuring some iron. So you see there are different values coming in your different experiments, right? And here lies the average 19.8 in some unit, and the other values are just on each side of the average. So it's a random fluctuation around the mean. Now, how the small individual undetectable become detectable random error? Actually, probability is at the fundamental. So let us define first what do you mean by distribution. As we have mentioned that there are so many errors, and in different combinations they come out. So the accumulated effects may be many in numbers. Out of those, a particular one, how many times it is occurred out of the total. So that is called the relative frequency of errors, which we can call the probability as well. That is probability of occurring of that particular cumulative error. And if you plot that frequency, relative frequency, against the different magnitude of errors, the cumulative magnitudes of different errors, that plot is called actually the distribution, right? So it will be clear in a while. Example, let us think of a small problem. 4 random errors are there, suppose, and each one is equally likely to occur. Now, each can cause an error either say plus u or minus u. So that means that it increases the value by u or decreases by u. So it can be shown that if 4 random errors are there, then there are 5 possibilities of getting the cumulative errors: minus, plus 4u, minus, plus 2u, and 0. That will be clear also while. And now the question is that how many ways these 4 random errors can be combined to give you minus 2u or plus 2u or 0, etc. So how many ways? Suppose that is each one is ni, and the total is sum over ni, that is capital N. So the relative frequency is nothing but this ni by n for ith cumulative n, that is either minus 4u minus q, etc. So that is the relative frequency. Now it would be even more clear that with this example we have mentioned that 4u is the possibility. Now that is only one way we can arrange all these 4 random errors, and if all of them occur in a positive plus plus plus, and that would give you 4u. So it is only one way. So the number of combinations is 1. But plus 2u or minus 2u, there are more than one combination. Plus 2u, how you can get? If you take 3 positive contribution from 3 errors and 1 negative from 1 error, and that cumulative effect is 4 minus 1, that is 3 minus 1, that is 2. But how many ways you can arrange? Out of 4, the first one can be negative, all remaining positive, or the second one can be negative, or the third one can be negative, or the fourth one. So these are the only 4 ways you can think of to get plus 2u cumulative. So it is 4. Similarly, minus 2u, it is also 4. Here 3 negative and 1 positive. The first one or the second one or the third one or the. But in case of 0, you see the combination can be 2 positive and 2 negative. So which are negative? It can be possibility that 1 and 2, error number 1 and 2, or 1 or 3, or 1 or 4, or 2 or 3, or 2 or 4, or 3 or 4. So it gives you 1, 2, 3, 4, 5, 6. There are 6 ways to get this combination. The total number of combinations is 1 plus 4 plus 6 plus 4 plus 1, that is 16. So relative frequency or probability of occurring of this particular 4u error is 1 by 16, of 2u error is 4 by 16, and so on. So these are the relative frequency values or probabilities, and we are talking about plot these values against these 5 different magnitudes, right? So it looks like this. So very interesting to mention here that though the errors individually are random, their outcome is supposed to be random also, but this particular distribution of random error, this relative frequency versus this one, it is not quite chaotic or absurd or random. It looks very systematic, right? So it's a good pattern, and this is for 4 numbers. Now if we increase, suppose there are 10 individual errors, that is an 11 combinations we get, and plus 11 minus 11, and this looks like false. So very close to this one. So but even more systematic, right? And initially similarly, if you take a large number of errors in hand regard, then this smooth graph occurs, right? So the relative frequency gives you this picture, and if you try to have a function which represents this graph or curve, it is like this. So y is y as a function, it becomes e to the power minus x minus mu whole square by 2 sigma square by this square. So 2 parameters are there in this equation. One is mu, the average or mean, and one is sigma, standard deviation, that we discuss later. And this is the so-called famous Gaussian distribution or normal distribution. But again, very interestingly, this is quite available in many places. Same distribution of the pattern of numbers. Say for example, if I ask you what is the formula of a plus b whole square, it would be easy for anyone to give a square possibility for this. 1, 2, 1. A plus b whole cube. So that is also obvious. A cube plus 3a square plus 3ab square plus 1, 3, 3, 1. These are the numbers. And this actually this is called binomial coefficient, and this is the binomial expansion. A plus b whole cube for n. N is any positive integer. And this NCR is actually this factorial n by factorial r into n. So this NCR actually gives you those numbers, and if you arrange, then you will get this triangle, beautiful triangle of numbers, and this is known as Pascal triangle. So a plus b whole to the power 0 is 1. A plus b, that means 1a and 1b, so 1, 1. A plus b whole square, a square plus 2ab plus b square. So a cube plus 3a square b plus 3ab square plus b. So a plus b whole to the power 4. If you ask the student, probably he or she will fumble, he can't remember. But from this triangle, it's very easy. It is actually a 4 plus 4a cube b plus 6 a square b square plus 4 ab cube plus b to the power 4. And similarly for any, so that gives the Pascal triangle, and very easy to write down the triangle, because 1 plus 4 is 5, 4 plus 6, 10, 6 plus 4 is 10, 10 plus 10 is 2. So we just add the previous line values and get the next line. This is very simple. So this binomial expansion is actually giving you this pattern. Why I am calling so? Because if you plot these numbers, by bar chart, you will get this kind of graph, and which is actually represented by Gaussian distribution. So there is a beautiful connection between binomial expansion, this permutation combination formula, this Pascal triangle, the curve, and the Gaussian distribution. Another quick example: gambling, tossing the coin. Is there any winning strategy for gambling? Suppose we have taken 4 coins. The head are valued as +1 and the tail are valued as -1. So what are the possibilities? There are 5 possibilities: 4 head, 3 head, 1 tail, 2 head, 2 tail, 1 3 tail, and 0 head, 4 tail. So there are only 5. So the values for 4 head is 4 into 1, 4. 3 head and 1 tail, so 3 into 1 -1, tail is -1, so that gives 2. And similarly, 2 head 2 tail gives you 0, 1 head 3 tail gives you -2, and all 4 tail is -1. So suddenly we'll jump that, okay, this is a very common and popular problem, because a few minutes back you have exactly proposed the same problem in terms of random error. Yes, that is my point, that there is a beautiful connection of the random error distribution and this tossing the coin game. They are exactly the same. So I can ask the question that, taking it as a gamble, that what should be the best bet on what total value? There are 5 possibilities. So every time you can have a bet. So on which value you should have your bet to have a better winning chance? That is the question, and that really can be predicted, and there is a good amount of agreement between the prediction and the right result. If you take really n equal to 100 or 1000, many big times. If you play many number of times, then really you can predict. So the questions can be like, is there any particular value most likely to occur? That is that value on which you will keep your bet, right? And what is that value? And is there any order of likeliness of the 5 possible values? Okay, leaving aside the best one, what are the other possibilities? So these are the questions and to be answered from the description. So for example, if I take here n means the number of points. So if I increase the number of points, then we play a number of times, then have a bar chart that all head and all tail and in between these values. This is the curve. It is a beautiful symmetric bar chart, because we are calculating theoretically by using the probability, right? Next, if you take 100 coins, then it looks like this. Again, it's a good symmetric curve and gradually approaching to what we call Gaussian distribution, and really it now becomes almost continuous curve, and n is 1000, and if n is really very large, you really get the Gaussian distribution, right? So that is the connection. So so far so good. We have only theoretical calculation based on probability and got the results theoretically. But what happens in real experience? Let us see. Really, it was done by some students over a number of years with 10 coins. So 0 head and 10. These are the possibility, and these are the numbers of times they have got that. Right. Actually, it is an experiment conducted over 18 years of period and done by 395 students. 395. So after getting the results, so they plotted 1, 1, 2, 2, 42, etc. These are the values against the number of heads. So 0 head to 10. So if you calculate the average of these values or the standard deviation, you can calculate by standard formula. And as I mentioned, there are two parameters, mu and sigma. So this superimposition of this Gaussian curve looks very fit for this graph chart, and they have the same mu value and same standard. So same mu and same sigma with this bar chart, Gaussian distribution fits very well set up, right? And another real life experiment, we are measuring some volume, and we have done suppose 50 times this experiment, this measurement, and we have got this type of possibility that from 9.969 to 9.971, then 972 to 974, and so on. And out of 50, they have got 3 times the first value, range of value first, only 1 for the second, 7 for the third, and so on. So total is 50. So if you calculate in terms of probability or percentage, then 3 by 50, 1 by 50, 7 by 50, these are the, and total is of course 100%. So these are the percentage in range. So you will finally plot these values, right? And if you plot, again you see that fits very well with the Gaussian distribution, same mean and same standard, right? So this is very interesting. Really. If you take a large number of values, this possibility large number, then really you will get a Gaussian distribution exactly coinciding or matching. So now it comes to the point that statistical treatment. So we have understood what random errors are there and how they relate to the binomial expansion, Pascal triangle, Deming problem, etc. Good. But how would you treat statistically this random errors? So before all, let us clearly mention our assumptions that random errors in analytical results follow a Gaussian or normal distribution. So from our experience, we have seen that in so many different types of experiments, this normal distribution occurs, right? So it's an assumption, justified assumption, that random errors in analytical results follow a Gaussian or normal distribution. But this is not the only distribution occurring naturally. There are possibility of another binomial distribution when the outcome is either or success or failure. This kind of output is coming. Then binomial distribution, that's a different, we will discuss. Another is Poisson distribution. It is mostly relevant to radioactive or proton counting experiments. The two we will not discuss here. But however, these two also can be approximated by Gaussian when the data set is large. So we are now coming to the analytical chemistry, and we start with population and sample. It's a very common idea that a population is the collection of all measurements of interest to the experimenter, while a sample is a subset of measurements selected from the population. So all possible measurements, if you really do, then the results collection is population, but it's not possible because of time constant. So what we do, we take not the whole but the part, so a sample, and that's why you call in subset of set. Set is the population and sample is the subset. So I do a selective measurements only, but our target is to infer on the overall population, but by studying only sample. So how far this is justified? Particularly if you keep it in mind that sample, if you take just a few data points, then the question whether it really represents the whole population. So that's a serious question. So you have to be careful, and moreover, all the statistical laws are derived for population, but we want to infer on population by from or from sample study, right? So we have to modify, need to modify those derived laws which are meant for population, but we want to apply it for sample, so we have need to modify them for sample. So how do we do that? What are those derived population laws, etc.? How really we can use meaningfully in statistical analysis and chemistry? That we will discuss in the coming. So thanks for watching. Our next video will be coming soon, and that would be the third episode of Exploring Statistics 3, and here we will discuss statistical treatment of random error. Till then, please keep on watching, do subscribe, and encouraging your friends to subscribe and enjoy the channel. So thank you very much once again.